Welcome everybody to today's talk within the Design++ speaker series provided to you by the Design++ initiative of ETH Zürich. My name is Michael Kraus and I'm happy to be your host today together with Daniele Grigo and Romana Rust. It is my special pleasure also to welcome our guest and the lecturer, Dr. Kian Wee Chen. And before I introduce to you our speaker and his talk, let me shortly provide some background information on Design++ and the IDL. The Design++ speaker series is a recurring event where we will provide invitations to upcoming events in due time via email, our homepage, or even our YouTube channel. You see the distinct list of speakers here, and you can also find updates on dates, speakers, and topics at our homepage. If you want, you can even subscribe to our calendar and automatically import the invitations to those events. You're warmly welcome to have a look at our YouTube homepage. There, as I said before, we would host the talks and videos of our previous speakers. The link can be found here. And as I said, you are welcome to have a visit. At the moment, there is a number of professors from architecture, civil engineering, but also computer sciences associated with the Design++ at ETH Zürich. For the running business, there is this core team of the three leading postdocs. We are responsible for running the Immersive Design Lab together with steering some research and teaching activities. A growing number of scientists and chairs and professorships is associated to the Design++. And if you're interested in the future and the connections of AI, machine learning, and extended reality with the AEC, then just reach out to us. We are happy to discuss any ideas or projects with you. Having said all that on the background of Design++ and the speaker series, I would hand over to my colleague Daniel for introducing the speaker of today.
Yes, thank you, Michael. So today I'm happy to introduce Dr. Kian Wee. He is currently a postdoctoral research at Princeton University, and I had a chance to discuss with him a bit about his research a few months ago, and I think he'll be a great addition for our speaker series. Today, his talk will be about the use of algorithms, models, and data in the design process. Kian Wee is also familiar with the ETH Zürich, where he did his PhD at the ETH Singapore Center in Singapore. And then he also joined the Singapore-MIT Alliance for Research and Technology, Center for Environment, Sensing, and Modeling. That's SMART-CENSAM. And he was a postdoctoral researcher there, looking at adapting and his integrated workflow for the urban design process. He also received the Distinguished Postdoctoral Fellowship from the Andlinger Center for Energy and the Environment at the Princeton University, researching the use of low-cost sensor and Internet of Things devices in the prototyping of building design and innovative cooling and heating. So with that, I really look forward to your talk, Kian Wee, and I'll hand it off to you.
Thanks for inviting me for this speaker series. I'm very honored to be here to talk about my project. So let me just see if I can set this up so that I can see people and my slides at the same time. Or else I feel like I'm just talking into the digital abyss without seeing people by the side. So today my talk is the use of algorithms, models, and data in the design process, as Daniel has talked about it. So before going into the talk, I'll just give a more brief background of my previous educations and my academia journey. So, all right, so I'm from Malaysia, but I work in Singapore, which is only 1 kilometer away from my hometown back in Malaysia. So I started my PhD, as Daniel has said, in SCC, Singapore-ETH Centre in the Future Cities Laboratory. So in my PhD, I work on the use of innovative cooling system in Singapore. So we kind of brought a bunch of new cooling system from Zurich, actually, and tried to adapt it for the hot and humid climate of Singapore. So, and then we built a physical prototype to test out the building system. So you can see we are quite hands-on, and kind of tested the system. So after my PhD, I went a few floors up to Singapore MIT Alliance for Research and Technology, the Center for Environmental Sensing and Modeling. So this is where, so in my PhD, I work on trying to integrate engineering system performance into the architectural design process. So in my postdoc, I try to kind of scale it up to try to kind of apply those techniques in the urban design process. In SENSAM, I work with a lot of non-designers, so like urban climatologists, and so during my stay here, I kind of was exposed to many different ways of working, and that kind of inspired me to look at things differently in my research. So after my postdoc, I got a Distinguished Fellowship from Andlinger Center for Energy and Environment in Princeton. So I flew halfway across the country, and where I am currently in Princeton. So again, in Princeton, I'm working with Forrest Magus, who is an ETH Zürich alumni too. So we went back into looking at radiant cooling systems and how do you more efficiently cool in the hot and humid climate. So again, we built physical prototypes to test out the system. So back to the topic, algorithms, models, and data in the design process. So within all those projects, I've always been kind of the guy at the back, handling or managing the models, the algorithms, and the data that's being collected in these different projects. And what is the objective of using algorithms, models, and data? So essentially, it is to be able to bridge the gap between different disciplines and enable designers to quickly get answers from models and data, and so that and streamline that whole process so that it's easy, to do it, and so that designers can actually concentrate and focus on the creative task. So, for example, you have a site, so now you can quickly draw an open geospatial data and get the site, and then you kind of push that model to for discussion, and then after discussion you might want to evaluate your site, let's say the solar analysis and so on, and that kind of spur discussion and collaboration between different expertise within the design team. You have a design solution, so you want to kind of push it to somewhere, push it and then get it evaluated. So essentially push it into a model and get it evaluated, and then discuss the result with other design expertise in the team. For example, mechanical engineer or envelope engineer and so on. And then you would kind of build up on that, have more solutions, and then have more performance, and this goes on, right? So you're iterating through improving your design and so on. But how do you make it easy to do? So that's kind of, I think, the ultimate goal of why we want to use algorithms, models, and data, is to make it really easy to do this, to get performance, to discuss, to collaborate, and so on, and push data between sessions, between different design stages, and so on. So in this series, of course, in this presentation, of course, I don't have the one solution for this. So this is kind of the ultimate objective goal that I want to achieve, to make this process as smooth as possible. But in this presentation, I'll present a series of 5 projects where I've incrementally tried to do that, to use models and algorithms and data to try to enhance design tasks in the design process. So for example, performing site analysis using open geospatial data so you can have a better idea of your site, doing evaluation of your solutions, parameterizing your design so that you can generate multiple design variants, and essentially, using some kind of search algorithms to kind of improve on it and explore more design process. So without further ado, I'll go into the project. So in the first project, processing terrestrial LiDAR scan trees for multidisciplinary analysis. So this was a project that I did with urban climatologists back in Singapore. So for him, he was doing some carbon accounting in Singapore. So but one of the problems is that he doesn't have good detailed information about above bioground mass for trees. So the way he's doing is just essentially measuring it using a measuring tape and then estimating and predicting kind of the carbon mass of the tree. So so in ETH Zürich, in FCL we have laser scanning terrestrial LiDAR scanner that's lying around. So we got our hands on it, and then we went out and did the scanning. And you can see on the right side is kind of like a typical scene that you'll get after a scan from a terrestrial LiDAR scan. On the left is kind of explaining what terrestrial LiDAR scanning is for people who's not so familiar. So essentially it's shooting out beams, and when it hits something, it returns, and then you kind of get one point in the physical space. So you can kind of create this whole scene of your interest. But the main issue with terrestrial LiDAR scanning is that it's unstructured point clouds. It's very hard to say, how to get the trees and how do you calculate the biomass and so on. So that's where I come in. So we went down to scan, and then I kind of tried to develop a way to extract out the tree of interest and take out the leaves, get the branches, calculate the carbon biomass. So what would this be good for? So for example, for of course, the most immediate use for this project was to do carbon accounting for a neighborhood in Singapore. It can be used essentially to, for example, using urban modeling in MVMAT, for example, to do CFDs and so on. And for remote sensing people, they would like to use the terrestrial LiDAR scan points for calibration with airborne laser scanning. So essentially, terrestrial LiDAR scanner is kind of regarded as the most accurate scanning technique. So I kind of developed a whole set of algorithms to do this. So to start with, the first thing is how do you scan a tree? So a tree of interest, you want to scan at least 3 points, three anchor points, so that you get all the facade of the trees. And then once you get the trees, you combine the tree scans together. And it's also important that what hardware you're using. So it's important that you need to get a specific wavelength of scanning so that it's easy to separate the leaves from the branches. So only certain wavelength scanner allows you to quickly separate the leaves from the branches. So once you separate the leaves from the branches, so this first 3 steps is kind of semi-automated. You kind of interactively cut out the tree and so on. But once you get to here and you use the right scanner, you are able to separate the leaves from the trees. Then you can skeletonize the branches, and then you can get the biomass of the tree. And you can also get the branching order, the architecture of the tree. So for any botanists or people who are studying trees, it might be interesting for them to study the tree architecture and so on. And so the skeletonized and then the tree volume essentially in this project was used in a carbon accounting model. And interestingly, what he found out was, or what not found out, it kind of just supported his claim is that trees are not carbon sink in tropical city. Trees is actually a carbon emitters. So the more trees you plant, they do emit CO2 because of, for example, the microorganism in the soil that's supporting the trees and so on. So it is still a net carbon CO2 emitters, which is opposed to some that say that planting trees can be a carbon sink in cities. So and also because trees in Singapore are pruned so much, right? So where does all the prune branches go? If they're going into the incinerator, so the CO2 is essentially released into the air again. So so through this, we were able to have a more accurate and more high resolution carbon accounting model where it can inform designers about the benefits of trees, right? So I'm not saying don't plant trees, but I'm just saying plant trees for the right reasons. So trees have many others a reason to do so, for shading, for aesthetic and so on. So this was one project where the use of these design techniques were able to help everyone understand the site much better. So in the second project is essentially a project that I did in Princeton, where after looking at open geospatial data, I tried to look at is it possible to construct the 3D model of a site of interest from just open geospatial data. So essentially, this is a project that tested that out. So we got in this project we got kind of the digital elevation model. We got the airborne LiDAR point clouds and so on, and the building footprints. And we were able to recreate the 3D environment of Princeton based on totally open geospatial data. And then we ran a solar analysis on the whole area. So, I mean, one of the motivation was because one of the physics students, final year project, she was interested in looking at powering personal electric vehicle on campus. Is it a viable option to move around campus with just solar powered, totally solar powered personal electric vehicle? So it's also because the facilities in Princeton campus drives around in this little golf cart here. So she was interested. So we installed like a solar panel on the golf cart and kind of optimize the engine for solar charging and so on. But essentially what I'm working on was to kind of create this 3D model of Princeton environment, which also have tree coverage and so on, so that it's possible to kind of collect data on the golf cart routes and figure out their use ratio, their use to parking ratio. And with the model and the solar analysis, you'll be able to find the optimal parking space. For example, if they park somewhere, make sure that it's not blocked and so on. So with the 3D model, you will be able to kind of do that. So because the main user of this kind of model is people not from architecture. So the idea is that if it's an architect, probably Grasshopper or Rhino is kind of accessible to them, but to a physics students and to a mechanical engineer who was installing the engine in the cart, it's just not possible to get them to learn Rhino, right? So what I did was I developed a visual analytics app where I uploaded the whole 3D model onto the app, and they can just download the app and then put in the data as they collect it, and so that they can kind of append data on top of each other. So this was to help collaboration between people from different disciplines. So hopefully this help that discussion when data are put together. But I mean, this was a project that I was working on, and then COVID hit. So now the physics undergrad has graduated. So it's kind of it stops here, and then we have been trying to revive the golf cart again and so on to kind of further push this project along. So the third project is, so it's not so much about representing the 3D the site, but in this project, it's about evaluating it. So if you have a representation of the site, a 3D model and so on, how do you evaluate it? How do you know that this region is performing how well in relation to the other region? So the idea was that to kind of find a bunch of indicators. So essentially a bunch of models that can inform the performance of a neighborhood, for example. So what I did was I found 5 indicators that is based on urban forms. So as long as you have the physical form of the geometry of the site, you'll be able to perform this analysis. So the first 3 is kind of like a solar base, where we look at so we run a solar analysis, let's say on a building, and then we kind of have a ratio between envelope facade area that's within a certain threshold and divide it by the floor area. So for example, if you have daylighting, you want enough daylighting on the facade to serve the floor area, right? So you normalize it by the floor area, and then you kind of have an idea of how well the envelope is performing. So if you run it on all of the buildings, let's say in a city, you can kind of roughly have an idea of how well the morphology of that whole area is performing in solar sense. So the other indicator that I did was a ventilation indicator. They call it frontal area index, where you project your building envelope to the wind direction, and then the frontal area is divided by the plot area. So you have an idea of how much wind the building is blocking. So again, if you apply it to a big region, you can kind of roughly have an idea of how well ventilated the neighborhood or this precinct is according to this indicator. So you want it to be as low as possible. Yeah. And this is a mobility indicator. So it's a route directness index. So the idea is that from one point to the other, how direct is it? So the more direct it is, the closer it is, the much easier for mobility. So essentially, usually a full grid is the best. So from any point to any other point, there's always multiple routes to get there, and it's really closest to the straight line route that you can find. So these are the 5 indicators. So what I did in this project was I tried to test out how sensitive they are to different morphology. So the idea is that if I have different typology mixed within a precinct, within the neighborhood. So let's say, for example, point blocks, so like tall blocks, and then or you have point blocks that have mixed height, and then you have courtyard typology, and then you have slabs. So if it's all, let's say example 1 is all point blocks, so how well they perform, and example 2 is a mixture of so that you want to know how is it able to detect and the change in morphology and how well they are performing. So I did this on 8 different examples of different settings and different typologies. So and then these are the results. So I mean, in short, it was able to detect morphological changes, but of course, I mean, this is it's kind of condensed into a single number where you can quickly see what's happening, but it's much more effective if you were able to go into the model and see why the indicator is so. So I mean, there's of course still a lot of room for improving what this indicator can be. But essentially, the modeling and the solar analysis, could still be used. So you can see in example 2, it's performing quite well in terms of daylight, the daylight availability, and for example 3, it's performing very well in terms of a frontal area index. So they're all the same density. They're all building in terms of the same density and so on. So depending on different morphology, it will be good for different, indicators. So for ventilation, for solar, and so on. So you can see the frontal area index is much better for the courtyard as compared to a mixture of point blocks and other typologies. And so so this is the root directness index. So if you use, of course, if you use a full grid, the root directness index is the best, 0.51 here. But if you just reduce it, so this is the road length, it's like 20,000 meters of road length compared to 9,852. And you only have a 0.07 reduction. So this is something that have to be, we still have to calibrate it with, empirical data, like what does 0.07 means essentially. But, it's a half reduction in half of road length, but the performance-wise, it's not that big significant, it seems so. So is this something worth pursuing and so on? So that kind of the set of performance would give a designer a better information to make decision. So this is kind of overall fitness-wise, this seems to be the best example and so on. So what I proposed at the end was that, in Singapore, so Singapore is divided into 51 regions and areas. So what we can do is we run this for all 51 regions, right? So we can have the idea of how each region is performing. And then we kind of try to calibrate it. What does this indicator mean? What does 0.13? What does 0.37 in daylight availability mean? So you kind of perform this indicator on a big set of data, and then have an idea, and then probably you have to go down and get some more data, real-time data than model simulated data, and see what exactly this number means. And then if it's possible, we can kind of set a national standards on what would be a good set of performance indicator to look at when you're designing for a neighborhood. So that's kind of like the motivation for this project to introduce a set of indicators that might be useful for planners. So the next two projects is mainly about applying these design technologies in the design process. So the previous three is more about evaluating and understanding the site analysis and the site. So these two is really applying it in design and how architects can use these design techniques in their design process. So in this project, I'm using multi-objective optimization to optimize building form and envelope and cooling system to improve building energy performance. So like this kind of is the main aim of this design technology is to kind of put it in the hands of designers and how they can use it. So first of all, you have in the multi-objective optimization process, you have to define your project. So the most classic and traditional or conventional problem in design of an envelope is the daylighting versus cooling. So the more daylight you let in, the more cooling it will increase the cooling load essentially. So so this is only in a tropical climate. So you want to kind of get the right amount of daylighting, but at the same time, not too much so that the cooling load is still within a good load. So in this optimization process, we are trying to look at the envelope design, and if we are using different cooling system, how would that kind of affect the envelope design with this? So we are comparing the two main types of cooling system, radiant cooling and air-based cooling. So you can see on the left side is radiant cooling. So essentially radiant cooling is cooling by radiative cooling. So you essentially cool down the surface of your interior, and that surface exchange remove heat from the occupants, as compared to air-based, where you kind of throw air into the space and then that air kind of cool down the occupants. So the main difference is that in radiant cooling, it uses less energy because as you can see in this diagram on the left side, radiant cooling uses 18 degrees Celsius cold water to perform cooling, and while air conditioning uses 8 degrees Celsius. So that increases in temperature difference between, reduces the need for cooling energy. But there's one limitation to radiant cooling, is that there is a limit, there's a capacity limitation. So because if you do not have enough surface, you can't cool the person, you can't sufficiently cool the person. And because of condensation issue, you can't use water, a chilled water that's too cold, right? So it has to be with above the dew point temperature. So there is a limitation, and there's a possibility that you do not have enough activated surface in the interior for you to sufficiently cool down the space. So that's kind of the issue here. And this was inbuilt into the optimization problem, the problem formulation, that the model, the thermal model that's being set up, actually check the activated surface, which is the ceiling. Is there enough ceiling surface area to install radiant panels to sufficiently cool the person when you're using? If it's not enough, it will use the air-based cooling, which is less efficient. And at the same time, we have another model that's looking at the daylight analysis, the daylight performance. So you kind of want to balance both of this in the in your design process. So so this is the two model that's evaluating the design solution. And then in the case study, it's kind of like an office building, a typical 5-story office building in Singapore. So first of all, you have to parameterize your design so that it's able to generate multiple design variants. So you can see how the design was parameterized. In A, you define 4 points, and then you create a footprint, and then you extrude it, and then you decide what is the window to wall ratio, the glazing material, and so on. So you can see the multiple design variants that's generated from a single parametric model. You put that parametric model into the optimization algorithm, essentially. So in the optimization algorithm, a solution is represented by a series of parameters. So for example, the window wall ratio, and the so the 4 points, the window wall ratio, and the window glazing materials, and so on. So in the optimization algorithm, essentially they crossbreed and mutate each other, and then when you combine two, you can get another two different design variants from the parent variants, and then you evaluate it with the two models, and then you only pick the strongest, so essentially the better performing, and then you will again put it into the optimization algorithm and breed them, and then so they will have stronger chow and so on. So essentially it's mimicking evolution, what we're trying to do here. And then you kind of generate stronger and stronger or better design. So here, each dot here is a design option. We generated 5 designs, and we just stop it. So it's mainly to explore, the relationship between envelope building systems and the design. So we can see that there's 4 clusters here, and the red dots are the Pareto front. So what is a Pareto front? So the optimal is essentially you want to reduce energy consumption and you want to increase daylighting. And this is the optimal region that you want to be in. And the red colors dot are the Pareto front that's kind of moving towards that region. So what's a Pareto front? So when you have multiple objectives, you can't say which, for design variants on the Pareto front, you can't say, let's say design A is better than design B because they're all on the Pareto front. So so that means they are dominated by no other design variant. So for example, in this case, H is being dominated by B. So because H perform both, worse in terms of, X and Y, right? But if you compare E and G, you can't say which one is better because E performs better than G in terms of Y, but G performs better than E in terms of X. So they are kind of equal. So they are all on the Pareto front. And that's a set of designs that you can look at if you're designing. So that's kind of the Pareto front. But I think what will be really interesting is to look at the clusters. So now we're going to zoom into the clusters. So in cluster 1, you can see they are very close to kind of the optimal region. And you can see they are very similar looking in terms of building form. So they are in Singapore, you are north-south facing. You have a long north-south facing facade and short east-west facing facade. And they are all kind of facing north-south and so on and east-west. And and then they kind of achieve a good performance. But if you're interested more in, let's say, more variation in terms of forms, you can look at cluster 3. Yeah, so it's not as good performing, but you can see it's still using radiant cooling. I'm sorry, so I kind of missed that. So they're still using radiant cooling, and they have more varied form. So it kind of trading off variability in forms to performances. So if you're really into performance, look at design from cluster 1 and try to design mimicking forms that's generated in cluster 1. If you are more interested in, let's say, you are willing to trade off a little bit of performance for more variability in design, you can look at cluster 3. So there is some flexibility where you can vary your form, and then you can look at it and try to design based on that. So in cluster 4 is the worst performing cluster. So essentially those are the buildings that's using air-based cooling. And you can see something very interesting is that if you look at, design variant 331, and you look at some of the good performing design variant cluster 4, they are very similar. And the only difference is the glazing material. So just because design variant 331 used a better glazing material, it was able to use radiant cooling. So that kind of quite valuable, right? So if, for example, the architect or the designer is I kind of want this kind of form, so they need to know that, oh, if you just use a better glazing, you can actually use a more efficient cooling system, and you can still kind of express your building form, but at the same time be able to perform really well energy-wise. So kind of running an optimization algorithm is useful for informing that, rather than giving you, for example, a specific design variant that you should take and develop, but rather is to understand the design problem at hand, because it helps you generate so many solutions. And if you kind of explore and sift through the designs, you'll be able to get some idea of what can be done and what cannot be done, and what will be the boundary of the performances and stuff. So so this is kind of this project. And once I did this project, I moved on to try to make this more accessible to students, because after all, setting up an optimization algorithm is still quite difficult, problem formulation and so on, and parametric model and parameterize your design and so on. It's still quite a difficult task, even with Grasshopper and so on. So in this project, I try to make it, for example, as streamlined as possible. So essentially, it's just to test out if the students were given this technique, would they be able to design better? So I have to remove those technical obstacles. So like teaching Grasshopper itself would take few weeks or even a semester. And then teaching an optimization algorithm itself would take. So what I did was I streamlined the whole process. I gave them a much simpler design problem. And it was only because it was only a 2 weeks workshop for students who are interested in exploring new design technology. So I give them this site where it's just a generic site, hypothetical site, where you have to build a tower in between, in the middle of it, and you have to optimize two simple objectives: the solar availability, so essentially the solar performance, to make sure that the buildings doesn't overheat, but it's still have good amount of daylight on the facade area. And of course, you want to optimize the floor area. And I gave them the script that would automatically calculate the performance based on this. So what they need to do was in the workflow, I divided the whole workshop into 3 main stages. So the first stage, I call it concept exploration. So they model some kind of messing in SketchUp. The SketchUp is kind of the easiest to pick up. So within the students, there's like year 1 students that have never touched CAD before. But I mean, because SketchUp is so intuitive, they were able to pick it up and model, simple design and put it into the script, and then it will spit out performance in terms of the floor area ratio and the solar availability. So you want both to be as you want to both maximize the 2 performance. So the first stage is quite manual. So you model it, you put it in, and then you evaluate. So that's kind of the first step. The second stage, I gave them a set of morphological operators, so they can twist and turn their design, messing, and so on. And that will kind of create multiple different design variant. And then again, so they would model the messing in SketchUp, put it into the script, and then they will specify a twist the tower, to in 45 degrees, or taper the tower, 1.2 value, and so on. So you can see once they put it in, and then they specify the parameters changes, morphological operators, they will generate like multiple design variants, and then evaluated based on solar availability and density. So, and the third stage, I call it algorithm assisted exploration, where the students, again, they always start with modeling kind of messing in SketchUp, and then they put it in and parameterize the building instead of specifying a single value. Now they specify a range, and then they put it into the optimization algorithm and run it for the night. And so you can generate a few hundred designs here, and then they can explore the design generated based on their messing model here. So this is kind of a submission of a student. So most of the students were able to do it, when the whole design process is kind of streamlined, but there's still some kind of freedom when they are doing their urban messing model, because they are building messing model, because they can still kind of create different messing and then parameterize it with my script. So you can see that they're trying to maximize both. You kind of have some design variants on the Pareto front, and they can look at it and decide whether it's useful to use, and what is the right parameters that they want to use for their design. So this is all the designs that's generated by the students in the 2 weeks workshop, because I asked them to submit their models and so on. So you can see it's like 5,000 designs that was collectively explored, and you can see some of the students' work that's on the Pareto front. Yeah, so I would say it's quite successful, because 27 out of 28 students were able to finish the exercise and generate quite a handful of designs and so on. But of course, I think the design problem formulation wasn't that well thought of by me. So if I was able to do it again, I would probably think of a better problem formulation for this problem. But so looking at what the students have submitted, so it's quite clear that as more design options are explored, they get better performing designs. So you can see on average, in stage 1, where you are manually modeling your design, the average number of design explored is about 7. Oh no, it's about 8. And then in stage 2, with the parametric morphological operators, it's about 28. And in stage 3, when the computer starts to generate for you, it's about 176. and you can see that the composition of Pareto front is that in stage, the Pareto composition of a student's design, like only 7% of the design variance on the Pareto front is generated from stage 1, and from stage 2 and stage 3 is 40 and 53%. So it shows that most of the design variance that's on the Pareto front is actually generated in stage 2 and stage 3 as compared to stage 1. So essentially giving the students the ability to quickly generate and narrow down design variance kind of help them to kind of really optimize that one concept or one solution that they were working on in stage 1. So that's kind of I think everybody knows that, but the thing is, I think this project kind of really give a more concrete example of, if you give the students the right tools, they can really exhaust the technique and be able to optimize their design much more if it was much easier to do it. I know with current, with the whole visual programming like Grasshopper and Dynamo, it's becoming easier and easier. So I think we're moving in the right direction, but I guess there's still a distance, because essentially parameterizing a design and so on is kind of more than the tools. Also, it's also about teaching them how to think about the design problem. So I guess that's kind of the end of my presentation. I will go back to the first slide of what I'm trying to achieve here. So I hope my project kind of illustrate the idea that models, algorithms, and data, it can be used in design process to enhance a lot of the stuff that we are doing. But I think currently the main issue here is how do you make it really accessible to different team members in your design team between different design stages. So how would, for example, in my example, the projects from the first 2 or 3 projects, after you kind of evaluated and represented your site, how does that go into your design stages? How do you use the site analysis and data or performance that you kind of understood from your site analysis in the design process? How does that, practically, and how does that data and model flow into the design process? How do you use that in optimization algorithm? So there is essentially a issue here with a lot of interoperability issue with different tools, different models, and so on in the design team. And that, I think, is essentially what we have to address. And I think once that's done, it will really change the way we design, where we can have really quick feedback with our solution proposal, and we can really think about how that change the whole design industry and profession as a whole. And thank you. That's the end of my presentation.
Great.
So I would quickly announce the speaker of the next talk. So thanks again for this interesting talk and discussion. As I said, so I think there is further points to be discussed on the role of generative design and performance-based generative design. Thanks for your time and your efforts. As I said before, I will upload the information and the video of this talk on our YouTube homepage. And then it's a pleasure to give an outlook on the upcoming talk. It is delivered by Dr. Nikola Marincic. He is at ETH at the moment, postdoc researcher, and he will talk about expectations and what big data does have to do with architecture and mastership. I think we are looking forward to that in about 2 weeks. And I thank you for your attendance and the attention, and see you next time.